Hello AP Chemistry and welcome to 7.3 Sizes of Atoms and Ions, right? So to be mindful, atoms means neutral, right? Ions are charged. Quick note about what we mean in terms of size, right? So it's important to know what we're talking about. What we're talking about, so when we have, let's say we have two atoms here, okay? This is where the electrons are distributed, right? And here we have our nuclei, okay? The distance between my nuclei, if my atoms are bonded, right, is known as my bonding atomic radius, okay? Here we have our non-bonding atomic radius, right, where we sort of estimate from the center, right, to what we think is the outermost edge of where an electron could possibly be, all right? When we are going to talk about the size, right, we are actually going to be talking about the bonding atomic radius, right? So it's not really a big deal, but it's good to know your terminology and definitions, right? So when we talk about size, we are talking about half the distance between the bonded nuclei, okay? And that's what we're going to call size for the duration of this chapter, okay? So when we talk about the size of a hydrogen, we are saying that it is 0.37 angstroms, going back to units we introduced in chapter 6. 0.37 angstroms, when a hydrogen is stuck to something else, that would be half the distance between the nuclei, between another hydrogen, I mean. So two hydrogens stuck together, 0.37 is half the distance between my nuclei, okay? All right, so anyway, this is a periodic table showing my trends for atomic radii. Now, if we look, right, we see that there are period trends and group trends. You need to know those trends and you need to be able to explain them, okay? So let's start with the easiest one, right? As we go down a group, what do we notice happens for all of our main group elements and for our transition elements also, for the most part? What happens? Right, as we go down a group, my radius increases. Now, what that means, right, is that the size of my atom gets bigger and bigger as I go down a group. And why does that make sense based on what we talked about in chapter 6? Right, as we go down a group, we are adding a shell, right? In that as I go from helium to neon, right, I'm going from 1 as my outermost shell to 2 as my outermost shell to 3 and then to 4 and then to 5, right? Which means that as I add that shell, right, the outermost edge of my atom automatically becomes bigger, right? And the other part of that, right, is that I now have more shielding happening inside also, right? Which kind of goes back to what we talked about in a previous slide. So, again, as we go down a group, my radius increases, 1, because I'm adding a shell, and that also means that that outermost shell is now more shielded from the pull of the nucleus, okay? As we go across a period, okay, and when I say across, I mean the way we read, so left to right. So across a period, what do we notice happens to my atomic radius? Definitely for my main group elements and mostly for my transition elements. Right, as we go down or across a period, my radius decreases. As we go across a period, my radius decreases. Now, that one is a tiny bit more thoughtful, okay? As we go across a period, are we changing shells? No, right? There is no changing of shells as we go across a period. We are, though, adding electrons to the same shell, okay? So as we add electrons to the same shell and a Z effective increases, based on Coulomb's law, there is an increased attraction between my valence electrons and my nucleus, resulting in a smaller radius, okay? So thinking back a little bit, right, we have that equation that says the force of attraction is approximately equal to my constant times Q1, Q2 over distance squared, okay? And again, the important part is being Q's over my distance, okay? Now, if we think about it, if we're adding electrons to the same shell, right, so let's say here's my nucleus. I don't know why I did that. Here's my nucleus, okay? Shell 1, shell 2, shell 3. Obviously, we know they're not circular orbits, but it gets the point across, right? So let's say that we are adding electrons here, okay? So we have these two electrons that shield this layer out here, right? As we add one electron, this electron has a certain Z effective of approximately 1. If we add another one, the Z effective is now approximately 2, right? which means that as we increase my Z effective, so increase my nuclear charge, and increase this, where we could say that this is like Q1, and this is like Q2, right? As we increase the charge of my nucleus, increase the number of electrons, right? Meaning we increase my Q1 and Q2, right? By default, what that means is we get an increased force of attraction, and the size of my atom gets smaller as we go across a period. Okay? All right. Let's move on and talk about cations and anions. So first of all, just thinking about what that means, right? If something is a cation, what happened to it? Right, it lost electrons. If something is an anion, it obviously gained electrons. Okay. Now, again, all of this is always going to go back to the fact that we have like charges, right, over my distance. Okay. So then, if we think about having lost electrons, so let's say that we had 10 electrons, for example, and let's say 11. Let's say we had 11 electrons and 11 protons, and now we have 11 protons and only 10 electrons. What's basically happening? Right. In this situation, we have an increased Z effective, right? Meaning my valence now feels more pull from the nucleus, right? We have increased my Z effective by losing an electron, or however many we've lost, right? Which means that there is a stronger force of attraction. Therefore, the size of my ion is smaller. The size of my cation is smaller than the size of the neutral atom. Okay, and the opposite is true, right, if we're talking about an anion. So let's say that, for example, we had something that had, we'll just stick with this number since that's what we have, right, and 11 electrons, and let's say that we, to turn it into an anion, gave it 12. In this case, right, if we compare our positive to our negative, right, we have decreased my Z effective, which means we have a decreased attraction between my nucleus and my valence, which means that the size of my anion is going to be larger than the size of my neutral counterpart, which is what this diagram is showing us, right? A lithium cation is smaller than its neutral, right? Sodium cation, smaller than its neutral, right? Over here, sulfur anion, bigger than its neutral. Chlorine anion, bigger than its neutral, okay? Now, let's say that we wanted to put the following in order by increasing size. You'll say, oh, well, how am I supposed to do that? I don't know what to do here. Well, first of all, we would need a periodic table, right? And if we had a periodic table, we would go find calcium and potassium and chlorine and sulfur, and we would find, well, okay, this would be easier if we had a periodic table. So let's go ahead and pull up a periodic table. So if we have sodium and calcium, so remember sodium plus 1, calcium plus 2, so let's go ahead and jot those down. So we have 19 and we have 20. So this one has 19 protons, right? This one has 20. Nope, this one has 20. Chlorine has 17 and sulfur has 16. Okay. Now, if we think about what this means, right, if this is, and so let's say that this is all the number of protons that they start with, that also happens to be the number of electrons that they start with. But if this is a K plus 1, how many electrons does it have? Right, that means it actually has 18 electrons. This one, if it's 17 protons and it's a minus 1 charge, it has, right, this one as a plus 2 has, right, this one has a minus 2. Exactly. So if we look here, this would be called an isoelectronic set of species. Right? Iso meaning same, right? So this is an isoelectronic set, which means that in order to determine their sizes, we're going to have to look at the number of protons. Okay? Again, going back to the idea of charges, right? If whichever one has the most protons is going to have the highest Z effective, which means that the valence is going to be most strongly attracted to my nucleus, which means that it's going to have the strongest force of attraction and the smallest size. So if we look here, right, this one wins, right? So calcium 2 plus is going to be our smallest, my bad, smallest. So actually, you know what? Let's rearrange that. So we're going to have calcium 2 plus. It's going to be our smallest. And next up, we're going to look for the next one, right? This will be potassium. And then the next up will be sulfur. Nope. The next up will be chlorine. And then sulfur. So now they're in order by increasing size. Yes? Fantastic. If we were just comparing sizes of actual atoms, right, that would be easier because we would just look at where it is on the periodic table, right? So for example, if we're comparing these, right, we understand, oh, period trend, neon will be the smallest, right? If we were comparing these, we'd be like, oh, group trend, this one, or this one as far as we have named ones, will be the largest, okay? The only time it's a little bit more thoughtful is if we have an isoelectronic set. All right. Thank you for listening. Be good, and I'll see you soon for ionization energy. Thanks. Be good. Bye.